Hey guys, in this video we're going to talk about Chapter 1, Section 2, Functions and Expressions. So before we get into the math, the problem solving, we need to recall a couple of definitions, okay? So the first definition that we're going to talk about is variable. So what is a variable? Well, a variable is just a letter or a symbol that represents an unknown quantity. So for example, x, y, theta, and mu, these are all letters that represent unknown quantities, okay? The next definition we have is a constant. Basically, a constant is just a number. It's just a fixed number or value. So for example, we have 1, 8, and -3 are all constants. The next definition is a coefficient. So a coefficient is going to be a number that's being multiplied by a variable. So for example, in this term right here, 3x, 3 is the coefficient because it's being multiplied by a variable x. 2y, 2 is the coefficient because it's being multiplied by a variable y. -3z, -3 is a coefficient because it's being multiplied by the variable z. And in this last example, 5 is the coefficient because it's a number being multiplied by the variables a and b. Okay, so that's a coefficient. The next definition I want to bring to your attention is term. So a term is anything that's stuck together with multiplication, okay? So a term could just be a single number. It could be a string of numbers and variables all being multiplied. So here's some examples. -4x is a term. If we don't see any symbol in between the number and the variable, it's understood to be multiplication. Okay, so that's a term. We could also have just a single number. 6 is a term. -3x squared y is a term. All of these things are being multiplied. -3 times x squared times y. This is a term. 4abc is a term. -6wy squared is a term. So those are all terms. Next definition is an operator. An operator is just an operation between terms. So for example, addition, subtraction, multiplication, division, square rooting, cube rooting, etc., etc. These are all operators. Okay, expression. This is what we're going to really focus on today. An expression consists of terms and operators. So for example, we could have 2y plus 3x plus 4. So the terms here are 2y, 3x, and 4, right? They're all stuck together by multiplication and they're separated by the operators. The operators here, we have an addition operator here, and we have another addition operator right here. Okay, so that's an expression, this whole thing right here, okay? Another expression, we have 3xy minus 1. So we have the term 3xy all stuck together with multiplication. We have an operator of subtraction, and then we have another term of 1 at the end, okay? An expression can just consist of a single number and no operator necessary. So 22 is an expression. It's a very simple expression. Or we could have something like this. 3x minus 4 all divided by 5. We have some terms. 3x is a term. An operator on top is the minus. 4 is another term. An operator that's separating the top from the bottom is the division bar. Okay, so that fraction bar means division. And then we have a term in the denominator, which is 5. So that is another example of an expression. Okay, our last definition on this page is an identity. So an identity is a statement that says two expressions are exactly equal no matter what number we plug in for the variable. So for example, these two expressions on the left and the right side of the equal sign are equivalent. And the reason is because on the left, if we use the distributive property, we can distribute that 2 in, and we get 2 times x plus 2 times 1. And therefore, the left side is identical to the right side. So no matter what we plug in for x, we're going to get a true statement. So this is an identity. Same thing with our next example. On the left side of the equal sign, we have like terms that we can combine. 3x plus 8x is equal to 11x. So this is also an identity because the left side and the right side are exactly identical. Okay, let's do some practice here. So we want to identify the variables, constants, coefficient, and terms in the expression. So the first one, we have 2w squared plus 3xy minus 8 plus 3x. So let's first identify the variables. So remember, variables are just letters or symbols. So the first letter I see is w, so that's a variable. And we don't need to square it, we're just looking for the actual letter, not whether it's being squared or not. I see an x, I see a y, another x. We don't have to write the x twice though, so our variables are w, x, and y. Okay? Our constants are going to be the numbers by themselves. So anytime you see a number by itself, it's a constant. So not attached to a variable. We have -8. I think that's the only one here. So that's our constant. Coefficients. So coefficients are numbers being multiplied by a variable. So the first one I see is 2, that's being multiplied by the variable w. Then I see a 3 that's being multiplied by xy. And I see another 3 that's being multiplied by x at the end, but I don't have to write the 3 twice. All right, and last is terms. So anything stuck together with multiplication, separated by plus or minus signs. Okay, so first term I have is 2w squared. That's all stuck together. Next one I have is 3xy. Next one I have is -8. And the next one I have is 3x. Okay, so those are all my terms. And let's do the same thing for this next example. So the first letter I see is x. The second letter I see is y. The third letter I see is z. And then z repeats there. So those are the variables. Constants are going to be our numbers that are alone without a variable. So the only one I see here is -3. Coefficients, the numbers being multiplied by variables. So I see 9. I see -4. And I see +2. Okay. Our terms, anything stuck together with multiplication. I see 9x squared. I see -4xy squared z. All of this is stuck together with multiplication. Okay. Then I see 2z squared. And finally, -3 is my last term. All right, so those are all my terms. Okay, let's talk a little bit about equivalent expressions, aka identities. So when one expression can be turned into another using legal math, okay, so like combining like terms, using the distributive property, adding fractions, etc., we call the expressions equivalent. So we can say that two expressions are equivalent, or we can say that you know, when one expression equals another, that's an identity. So two ways of saying the same thing. Now let's look at our first example. It says, are the expressions -2 times x minus 4 and -2x minus 8 equivalent? Well, which expression are we going to manipulate? We can't do anything to this right expression. -2x minus 8, I mean, that's pretty much done. You know, it's, I mean, we can factor if you know how to factor, but, you know, we haven't really talked about that yet. So what's the better one to manipulate is the first one right here. And we can use the distributive property because we see a -2 being multiplied on the outside because there's no sign right here between the 2 and the parentheses, so that's multiplication, which means that we can use the distributive property. And the distributive property says, hey, we're going to multiply -2 by x, giving us -2 times x. And then we're going to multiply negative 2 times negative 4. Now a negative times a negative is a positive, so that's going to give us positive 8. So what this is really asking, is negative 2x plus 8 equivalent to negative 2x minus 8? And the answer is no, because of the subtle difference between the plus and the minus sign here. The expressions have to look identical for them to be equivalent. These are not identical because of that sign change. The plus and the minus sign are different. So the answer here is no, they are not equivalent. Okay, let's look at our next example. Is x over 5 plus y over 5 equal x plus y over 5 an identity? Another way of writing this is this equivalent to this. Are those two things equivalent? Well, on the right side, we have x plus y all over 5. On the left side, I can use, I can add fractions here to make it look different. So I have the same denominator. And since I have the same denominator, I can combine the numerators and put them all over the same denominator, 5. So x over 5 plus y over 5 is the same thing as x plus y all over 5. So is that an identity? Well, yeah, because the left side is definitely equal to the right, and we just used our mathematics to prove that. We know that when we add fractions with the same denominator, we can combine the top. So the answer here is yes. Awesome. Okay, let's go ahead and look at this. Which of these equations are identities? So we have 4 of these equations to look at. Looking at the first one, do we have like terms that we can combine? 2x squared plus 3x cubed, is that equal to 5x to the 5th? What do you guys think? Well, no, because they're not like terms. Remember, like terms have to have the same exact variables and the same exact exponents in order to combine them. Here, the exponent is 2, the exponent is 3 in the second one, so we cannot combine these. And so, because of that, we cannot do anything to the left side of this equation. It's simply 2x squared plus 3x to the 3rd. There's no combining to do. And for that reason, this is not an identity. Okay, let's look at number 2. We have 4h squared plus 3h squared equals 7h squared. Is that a true statement? Well, looking at the left, we do have like terms here because we have the same variable h in both cases, and we have the same exponent on each, 2, in both cases. So 4 of something plus 3 of something is indeed going to be 7 of something. So 4h squared plus 3h squared is 7h squared, and that is equal to the right side. So yes, this is an identity. Let's look at number 3. So here we have 2ab squared plus 3a squared b. Does that equal 5a squared b squared? Well, do we have like terms? Can we condense this some kind of way? Well, we don't have like terms because although the variables are the same, the exponents need to be the same on the same variables. So like, 2ab squared and 3ab squared would be like terms because we have the same exponents on the same variables. But since we don't have that here with 3a squared b, we cannot combine these. These are not like terms, and therefore this is not an identity. Okay, and number 4, we have 3b plus 2b squared. Can we combine these to make 5b cubed? Well, the answer is no, because my term 3b to the first and my other term 2b squared are not like terms. The reason being, in the first term, the exponent is 1, and in the second term, the exponent is 2. So they cannot be combined. So this is not an identity. Okay, let's do some more practice here. All right, so we can say so functions and expressions behave the same way mathematically when we're talking about, if two functions are the same. It's the same process as looking at if two expressions are the same. So are the functions f of x equal x squared plus 6x plus 10 and g of x equal x plus 3 squared minus 4 the same functions? So we really just want to look at the right sides of the equal sign. So in the first one, if you look at x squared plus 6x plus 10, you want to ask yourself, can I simplify this anymore? Can I combine like terms? Can I use the distributive property? Can I do any of these things to make it look a little bit simpler? And the answer is no. We can't really do anything here. We have three terms, x squared, 6x, and 10. None of them are like. We don't have any kind of distributive property or adding fractions or anything like that. So we have to leave it. So that has to stay as it is. Now this guy, we can simplify, right? The reason is because x plus 3 squared, what does it mean to square something? Well, it means to multiply it by itself twice. So x plus 3 squared is the same thing as x plus 3 times x plus 3. So what I just did is I carried this same thing down here, but instead of writing x plus 3 squared, I wrote x plus 3 times x plus 3. That means this exact same thing. So that's one thing I can do there. Whereas with the first function up here, I couldn't do anything. But here I can actually expand it out. So once you expand it out, you want to employ the FOIL method. So first, outer, inner, last. And if you need a refresher on this, I did make a video about this and some other refresher topics. So first, outer, inner, last. First, x times x is x squared. Outer terms, x times positive 3 is positive 3x. Inner terms, positive 3 times x is positive 3x. And finally, last terms, positive 3 times positive 3 is a positive 9. All the while, the minus 4 stays in the back. Now we want to combine like terms. So these guys are like terms here, and these guys are like terms here. So 3 of something plus 3 of something is 6 of something. So 3x plus 3x is 6x. 9 minus 4 is 5. So this is as much as we can simplify. So this was g of x. So the question is this the same thing as f of x? And the answer is no. The key thing that differs is in f of x, we have 10 at the end, and in g of x, we have 5 at the end. So these are not the same function. Okay. Let's look at this next example. So are the two expressions t squared minus t times t minus 2 and 2t equivalent? So can we do anything with 2t? No, that is a really simple expression. It's just a simple term. We can't do anything there, but we can manipulate the first one to look a little bit cleaner. And I can do that by using the distributive property. Now, if it helps you, what you can do is you can, before you do the distributive property, to make it look a little bit cleaner, you can actually move this t squared to the back, because remember, he's positive. He doesn't have a plus sign in the front, but he is positive. And this negative belongs to that t, so it needs to stay there. This negative t is the thing that's being multiplied in the front. So I'm going to just put this t squared in the back, and it's being added, right? We don't need to put the plus sign if it's in the very front, but if I put it to the back, I need that plus sign to indicate that, yes, it is being added. So I didn't do anything yet. I just moved the t squared to the back. And now what I can do is I can use the distributive property. I want to multiply negative t by t. So negative t times t is negative t squared. Negative t times negative 2 is a positive 2t. And then I still have that plus t squared in the back. Now, if I have negative 2 plus 2, isn't that 0? All right, same thing applies here. Negative t squared plus t squared, opposites, when you add them together, they go to 0. So that's 0, and we're left with 2t. So yes, these are equivalent because when we did the manipulation, we ended up getting 2t. So the answer here is yes. They are equivalent. Let's look at this next example. We have fractions here. Is 2 over a plus 3 over b equivalent to 5 over a plus b? Oh, don't do this. This is a really common mistake that students make. And, you know, it doesn't matter what grade or how old the students are. It's just, I see it all the time. So, remember, guys, when we add fractions, we need to have the same denominator. We cannot just add straight across. That is highly illegal. So here, we can't really do anything here. It's all combined already. But here, if I want to add these properly, I want to get a common denominator. And since we have two different variables in the denominator, to get the common one, we can just multiply them together. So the common denominator between a and b is just a times b. So I'm going to put my first term there. So 2a and then 3 over b. So what do I have to multiply a by to get ab? I have to multiply it by b. So I do the same thing at the top. So I get 2b over ab. And then for 3 over b, I have to multiply by the bottom by a. So I get 3a. So now I can combine these because I turn 2 over a into 2b over ab. That's the same thing as 2 over a. It's equivalent. So, and same thing here. So 2b over ab plus 3a over ab is equal to, well, 2b plus 3a over ab. This is how you properly add these fractions. So no, this is not equivalent because that's not how we add fractions. Okay, let's go ahead and look at this last one on this page. Is the square root of x squared plus 9 equal to x plus 3 an identity? Okay, so the square root doesn't have the property where we can separate the terms under the square root with addition. So in other words, this is a mistake. The square root of x squared plus 9 is not equal to the square root of x squared plus the square root of 9. It's not, they're not the same, okay? And how can you prove this to yourself? Well, what you can do is you can plug in a sample value for x to see if it makes sense. So like, what if I said x equals 2? If x equals 2, what would happen? Well, I would get 2 squared plus 9 equals 2, just plugging in 2 for x, plus 3. Remember, identities are true for all values of x. Now, the square root of 4 plus 9 is the same thing as the square root of 13. Does that equal 5? Well, no. If you put the square root of 13 in the calculator, you're going to get about 3.6. And so that proves, because, you know, this, wait a minute. Let's see what happened here. Yeah. Okay, so this proves that it's not an identity because the thing that we get on the left is not equal to the thing that we get on the right. So the answer is no. This is not a property that we can do with square roots, unfortunately. Now, if this was multiplication, we could, but since we have addition under, we can't. So this is not an identity. Okay, the next thing we're going to look at is translating words into algebra to answer certain questions. So let's look at this first example. It says, write an expression for the sequence of operations. So the first thing we want to do is subtract 3 from y. So we have y, and we want to subtract 3 from it. Okay, so that's my first operation. Then the second thing says double. So I want to double whatever I just got. So double means multiplying by 2, that whole thing. And finally, add 7. So we're going to add 7 at the end. Okay. Okay, so that is our expression that represents these words. Let's look at the next one. So we want to write an expression for the statement twice the difference of 3 times a number and 7. So let's underline the keywords here. Twice the difference of 3 times a number and 7. Now it doesn't tell us what the number is, so let's just use x as our number. Now, we want to do twice the difference of 3 times a number and 7. So 3 times a number, so that's 3x, and 7. And we want to do the difference of these because we want to take twice the difference, not just twice 3 times a number, but twice the difference of 3 times a number and 7. So 3 times a number x and 7, and then we're taking twice the difference of it. So twice the difference of 3 times a number and 7. And that is our expression there. Okay, let's look at the next one. Write an expression for the following statement: half the sum of a number w and 3. So sum means add, right? And difference means subtract. So a number, w, so that's w and 3. We're taking the sum of these two. And then we're going to take half of it. So half of it just means we can multiply by a half or we can divide by 2. Either way, it's the same thing. That's our expression there. Okay, so let's go ahead and do some word problems here. So it says the price of a visit to the dentist is $150. If the dentist fills any cavities, there's an additional charge of $50 per cavity. If the dentist finds C cavities, what's the cost of the visit? So the cost of the visit is going to equal something, right? Now, we know that the fixed value here, our constant, is 150. So that's, if you walk in the door, it doesn't matter if you have no cavities and you have perfect dental hygiene. You still have to pay $150, right? So we know that we're going to take 150 and add it to something that depends on the number of cavities we have. Now, if we have one cavity, we're going to be paying $50, right? 150 plus 50. If we have 2 cavities, we're going to be paying 150 plus 50 times 2, right? If we have 3 cavities, 150 plus 50 times 3, etc., etc. If we have C cavities, we're going to be paying 150 plus 50 times C. So that's going to be the cost of our dental visit right there. And C represents the number of cavities. So if we only have 1 cavity, we plug in 1 for C, and we get the cost is $200. If we have 2 cavities, the cost is going to be $250, and so forth. So that's our answer there. Okay, let's talk about this one. Assume that movie tickets cost P dollars for adults and Q dollars for children. A family of 2 adults and 3 children has an entertainment budget equal to the cost of 11 adult tickets. An adult ticket costs twice as much as a child's ticket. And so the question is, how much money will they have left after seeing 2 movies? And so the money is going to be in terms of the child tickets. Okay, so this is a lot to digest. What I recommend for word problems like this is just drawing a picture of what's going on and just kind of like listing what you have in like an ordered kind of fashion. So first of all, I'm going to draw the family. So the family consists of 2 adults. So here's my 2 adults. They're tall, I guess. And 3 kids. So here's my family. Here's my little family here. My 3 kids and my 2 adults. And the budget is going to be the cost of 11 adult tickets. Now, the adult tickets are P dollars for one, so the budget is going to be 11 times P. Sorry guys, if you hear my cat, that's her. She's being annoying. Okay. So here's my budget, here's my family. We know that, let's just write out what we know. Okay, so we have the family, we have the budget. We know that adult tickets cost P dollars for each one. Maybe I'll just do ticket here. And then children's tickets cost Q dollars. Okay, so this is some information we know. We have the family drawn. What else can we add here? We have the budget. The last sentence says an adult ticket costs twice as much as a child's ticket. How can we write this algebraically? An adult ticket costs twice as much as a child's ticket. Well, if an adult ticket's P, and P is twice as much as a child's ticket, so that's going to be 2 times Q, right? If a child's ticket is $5, if Q is 5, then an adult ticket is $10. If Q is 3, then an adult ticket is $6, and so forth and so forth. So that is something that we know from the last sentence. And let's get to the question. How much money will they have left after seeing 2 movies? So how much are they going to pay for 1 movie? That's the question. So pay for 1 movie. For 1 movie. And then we want to see for 2 movies. Right? That's what we want to identify first, because it's saying how much money will they have after seeing 2 movies, so we need to figure out the cost of them seeing 2 movies. Okay, so 1 movie. Well, we have 2 adults. This is adult 1, adult 2, and then we have 3 kids. So for 1 movie, how much are we going to pay for the adult tickets? Well, adult tickets cost P bucks. So we're going to be paying 2 times P bucks plus 3 kids times Q bucks. So that's the cost of 1 movie. So isn't the cost of 2 movies going to be 2 times that? Yeah, so the cost of 2 movies is 2 times the cost of 1 movie. Let's simplify this out a little bit. Okay, so we want to distribute that guy in there. 2 times 2p is going to be 4p. 2 times 3q is going to be 6q. So this is the cost. This is the cost of 2 movies for the family. And okay, so how much money will they have left over? Well, this is what they have initially for the budget. So they have this much money stocked up, 11p, whatever that is, who cares? 11p could be, you know, I don't know, 110 bucks. It doesn't matter what it is. It's 11p. That's how much money we have to start out with. And we go and see the 2 movies. And so what does that mean in terms of like how much money we have left? Well, we got to subtract, right? We take what we start with in our budget, which was 11p, and then we're going to take away the cost of the 2 movies. Now, the cost of the 2 movies is 4p plus 6q, right? So I can distribute this minus in there. I get 11p minus 4p minus 6q. Combine like terms, which are the p's. 11p minus 4p is 7p minus 6q. So what did we just find? This is the money left after seeing 2 movies. That's the money left over after seeing 2 movies. And what we want to do we want to get it in terms of Q, because we're asking how many child tickets does that money amount to? Like how many Qs do we have left basically? Now, look at our answer. We have P and Q in here. We don't want P. We want everything in terms of Q. How do I get the 7p to go away and put it in terms of q? Well, we use this fact that we got from the last sentence in our word problem. It says that p is the same thing as 2q. These 2 things mean the same exact thing. So, whenever I see a p, I can replace it with 2q. I see a p right here, I can replace it with 2q. Right? So this becomes 7 times 2q minus 6q. And again, this is the money left after seeing 2 movies. So 14q minus 6q is going to be 8q. So this is going to be 8 times the cost of a child's ticket. So this answer here is going to be 8. Okay, can they see a third movie? Can they see a third movie? Well, okay, so this is the money we have left, is 8 times Q. And what does a movie cost again? Because they've already seen 2 movies and they want to say, oh, well, can we see one more movie with the family? And look, this was the cost of 1 movie, 2P plus 3Q. Now, what our answer is just in terms of Q. So again, we can replace this P with 2Q here, right? They're the same thing. So 2P plus 3Q. If I go ahead and replace P with 2Q, this is 2 times 2Q plus 3Q. So this is 4Q plus 3Q is equal to 7Q. So now we know that the cost of 1 movie is equal to 7 times Q. And we have 8 times Q money left over. So can we see a third movie? Well, yeah, it only costs 7Q. We have 8Q. So yes, the answer is yes, we can see a third movie here. All right, let's do another example. Write an expression for the sales tax on a car. The tax rate is 4%. The price is $4,000 off the sticker price P. Okay, so how do we find tax? We multiply it by the cost of the item. What's the cost of the item? Well, the cost of the item, they tell us, is $4,000 off the sticker price, which is P. Who knows what it is? It could be $40,000. It could be $30,000. We just know that it's P. So 4,000 off is going to be minus 4,000. Yes, Pam. Sorry, guys. And finally, what we need to do is to get the sales tax, we need to multiply by 4%. Now, 4% is the same thing as 0.04, right? Remember what we do? We move the decimal 2 units to the left. So 1, 2, fill in the empty spots. So this is going to be our expression for the sales tax. 4% of the cost, and the cost is the sticker price minus $4,000. Okay, so that's our answer right here. Let's do one more. The number of registered voters in town A is X, and the number in town B is Y. If 37% of the voters in town A and 50% of those in town B are registered Republicans, write an expression for the total number of Republican voters in both towns. So since the total number of voters in town A is X, we know that 37% of those guys are Republican. So 37% as a decimal is 0.37. And then we're going to add on 50% of Y, because Y is the total amount of people in town B, and 50% of those people are Republican. So this is going to be our expression for the total number of Republican voters in both towns.